work on circumvention of tracking protections by means of first-party tracking. This is work together with Gunesh from COSIC, Lukas, an independent researcher, and Wouter and Tom from Disrenet. Okay, so when we think of online tracking, the first thing that comes to mind is cookies, because this is probably the most widely known and widely used method of online tracking. So whenever a user visits a web page, the browser will store all kinds of cookies. Some of them are essential and provide functionalities that are necessary for the website to function in a correct way. These are typically called session cookies and are first party, which means that they are set by the website which the user is visiting. However, there are also other kinds of cookies, such as tracking cookies, which store a unique identifier for the user, and they can be used in a first-party context or a third-party context. And what I mean by that is that the cookie can be set by the website that the user is visiting, but it can also be set by an external third-party tracker. So why is it important whether a cookie is first-party or third-party? Well, because of the same origin policy, which is a security measure built in browsers, which prevents resources from being accessed by domains that are different than the ones that owns it. So in the case of cookies, a first-party cookie cannot be accessed by an external domain. So how does third-party tracking work? Well, in general, when a user visits a certain website, the browser will issue a request to the server of that website, but also to the tracker that is embedded on the website. So in this case, it's to tracker.com. Together with the response, the tracker is going to set a cookie containing the unique identifier for the user, which is then stored in the browser. And every cookie is set under a specific domain, so which is why the same origin policy is important. So in this case, the domain is tracker.com, and the identifier is ID is 123 for the specific user. So the next time that the user will visit a different website, which includes the same tracker, the cookie will be sent together with a request to the tracker. So this way, the tracker will know that it was the same user that visited both these websites. And this allows trackers to build a profile of our browsing behavior on the web. So in this case, the key players are the publishers, so the websites who are showing us content, and these publishers make use of the services of trackers and advertisers. So trackers are collecting information about our browsing behavior, and this data is sometimes used by the advertisers to provide us with targeted ads. So this is obviously a problem for us users who want to protect our privacy on the web. So luckily, there are some tools out there that can protect our privacy. So on the one hand, we have browser extensions. I'm naming a couple of examples here: AdBlock, Plus, Privacy Badger, and Ghostery. These are all extensions that you can install in your browser that aim to block third-party cookies. So they do this by blocking the requests to trackers altogether. On the other hand, there are also browsers which offer built-in tracking protections. The first one is Safari, which has its own tracking protection, which is called Intelligent Tracking Prevention. And the way it works is basically it deletes cookies that have not been used for some time. So on websites that you have not visited for a while, the cookies are deleted and therefore no tracking is possible. On Firefox, Firefox provides built-in by default blocking of third-party cookies, and Chrome does not provide any by default protection at the moment, but they are planning on phasing out third-party cookies in the future. So that's why I mention it here. So on the one hand, we have publishers, trackers, and advertisers who are aiming to monetize content that is shown to us users, versus the users who use browsers and privacy protection tools to block these trackers and protect the privacy of users online. So as a reaction to tracker blocking tools, trackers come up with different kinds of tracking techniques to circumvent the protections that we are using. So one of these is first-party tracking. In this case, the cookie is first party, so it is set on the same website as the user is visiting, and the tracker aims to provide insight on the browsing behaviors of the user on that specific website. However, a limitation of this method is that it cannot be used to track users across different websites because the cookie stays first party. However, in practice, when this technique is used in combination with persistent tracking, it is possible to track users across different websites, such as, for instance, fingerprinting or cookie syncing, which I'll come back to later. So our work studies a specific kind of first-party tracking, which is called Cnamebased tracking. But in order to understand how Cnamebased tracking works, I will first explain a little bit about DNS. So when we type facebook.com in our browser and want to visit facebook.com, how does the browser know what the IP address is of that website? Well, the answer is DNS. So at DNS level, the browser will send a query to facebook.com, and the DNS resolver will answer with the specific IP address for the browser to navigate to. If I don't feel like typing facebook.com entirely and I just want to type fb.com, but Facebook still wants to provide a way for users who only type fb.com to still end up on the website of facebook.com, well, in that case, Facebook can use a CNAME record to link different domain names. So at DNS level, a query will be issued to fb.com, and the DNS resolver will return a CNAME record containing the alias for facebook.com. And then the browser knows, oh, okay, I have to do another query for facebook.com, and then I will obtain the correct IP address. So essentially, a CNAME record is a way to link multiple domains with each other. So how does Cname-based tracking work? Well, it uses a CNAME record to link a first party of the website itself with a tracker. So instead of issuing a request directly to the third-party tracker, as is done in third-party tracking, so here a tracking protection will block this request. Instead, a request is issued from the website itself to a subdomain of the same website. So in this case, it's a request from example.com to track.example.com. So this is a first-party request, and the cookie that will be set is also first-party and is set by the domain of the website itself. However, at DNS level, a CNAME record is used to connect the subdomain of the first-party website with a subdomain of the tracker. So in this case, track.example.com is connected with x.tracker.com via a CNAME record. So again, as with first-party tracking, because this is a type of first-party tracking, the limitation is that it's not possible to track users across different websites because of the cookie being first-party. So I will now explain how we were able to detect CNAME-based tracking. Well, first of all, we need CNAME records, and not just any CNAME records, but first-party CNAME records that point to a third party, because again, in CNAME-based tracking, a first-party subdomain of the website is connected to a third-party tracker via CNAME record. For our analysis, we used the public dataset of HTTP Archive, which is a monthly crawl of millions of popular websites. So we use this dataset to obtain first-party requests to a subdomain of the same website. Again, because that's the way Cname-based tracking works. Combining these two steps, we were able to create a list of Cname-based tracking candidates, but because not all services that use Cname trackers are actually doing it, not all services that use Cname records use it with a tracking purpose, we need to filter out just the services that are using this technique to track users. For this, we performed a manual analysis. So for each of the tracker candidate websites, we visited them and we looked for references of them using tracking or analytics as a service, or whether they were providing some other service that requires tracking. And this way we obtained a list of 13 manually verified trackers. And for each of the trackers, we were able to build a tracker-specific fingerprint, allowing us to distinguish Cname-based tracker requests. So this could be, for instance, the same tracking script being accessed again and again. In the last part, we ran an additional crawl with a different user agent, namely Safari, because of the intelligent tracking prevention I mentioned earlier. And we found that there was one tracker that was specifically present on with the Safari user agent, but not with Chrome, because Chrome does not implement by default blocking of third-party tracking. So, and they also brand themselves as a tracker that is used to circumvent Safari's tracking protections. So we obtained a list of 13 trackers, some of them bigger, some of them smaller. So we note the number of detected customer websites that were using this technique. However, this is an underestimate, because when we look at the actual total estimated number of publishers using the tracker, then we have a much larger number. We also noted the price that they were asking for this service, if it was available on their website. And finally, we had a look whether the uBlock Origin extension on Firefox and Chrome was able to block this tracker, and whether the NextDNS Cname block list, which we also use to extend the list of trackers that we use in our study, was able to block this tracker or not. So it is important to note that some trackers were blocked on Firefox by uBlock Origin, but not on Chrome. This is because uBlock Origin has implemented a defense at DNS level, where they resolve the request, and then they look at the DNS data to determine whether the request is issued to a tracker or not. However, this is technically impossible to implement in Chrome because of the limitations of the DNS API in Chrome. Second, the 3 of the largest trackers that we found were not included in the NextDNS Cname block list, which shows that our method was able to find Cname-based trackers that were previously unknown to tracker protecting tools. We had a look at the popularity of publishers that were using Cname-based tracking according to their Tranco ranking, which is a popularity index of the website. And we see that the distribution is heavily biased towards more popular websites. So nearly 10% of the top 10,000 most popular websites on the internet include a Cname-based tracker. We further looked at the different categories of the websites that are using Cname-based tracking. And as a baseline, we took the categories of the different websites in the Tranco top 10,000 most popular websites. And we see that more than 40% of the websites using Cname-based tracking are actually business websites. So to recap, we found more than 10,000 publisher websites using Cname-based tracking. Most of them are business websites, which explains their incentive to monetize the content that they're offering. nearly 10% of websites in the 10,000 most popular Tranco websites use a CNAME-based tracker. Our method allowed us to find 13 different CNAME-based trackers in varying size and customer base, some of which were previously unknown to tracker blocking tools. I will now talk about the historical evolution of CNAME-based tracking. In order to achieve this, we again used the public dataset of HTTP Archive, which is the monthly crawl of millions of websites. And for this, we used a recursive approach. So starting from the most recent month of our analysis, we go back and we base the amount of CNAME-based tracking in the previous month. We base it on the amount of tracking that is used in the current month. So in this way, we create a recursive approach to measure all CNAME-based tracking. And here we can see the results of our analysis. So during our 17-month period, we see that the use of CNAME-based tracking is increasing. So the blue line is here websites that are using a CNAME-based tracker with a CNAME to the same website. So for instance, example.com is issuing a request to track.example.com, and cross-site is whenever the website was issuing a request to another domain, but however still a related website. But the most important line is the green one, so the total number of websites that are using CNAME-based tracking, and we see that it is steadily increasing over time. So we wanted to compare the use of CNAME-based tracking to third-party tracking. So for this, we had a look at the most popular websites, and we see that throughout the measurement period, the use of CNAME-based tracking on popular websites has increased by 21%, while the use of third-party trackers that are popular remains stable, and the less popular ones is slowly decreasing. To further get an understanding of the effects of CNAME-based tracking on third-party tracking, we have a look at the evolution of third-party tracking. So we had a look at websites that recently became publishers and started using CNAME-based tracking. More specifically, we had a look at websites that were not using CNAME-based tracking for 6 consecutive months, then became a customer and used CNAME-based tracking for at least 6 more consecutive months. So we measured the number of third parties along this period, and we see that the number of third parties isn't changed, which indicates that CNAME-based tracking on these websites is not really meant to replace third-party tracking. It is actually used on a complementary basis to obtain extra information about the users visiting their website. So with the CNAME-based tracking scheme, there come some privacy and security implications, which I will discuss now. First of all, it is important to note that all of these privacy and security issues are only possible due to the way that the CNAME-based tracking scheme is implemented. So due to the fact that the tracker is included on the same website as the website the user is visiting. So from there arise the issues. First of all, we had a look at cookies leaking to the third-party tracker, to the CNAME-based tracker, sorry. So this was because cookies that are set by other first parties or by the website itself are scoped to the domain of the website. So we had a look at almost 9,000 websites that were using CNAME-based tracking, and we found that on 95% of them, at least one cookie was leaking to the CNAME-based tracker. So in the table, we see the most common origins of the cookies that were leaking to the CNAME-based tracker. So for instance, Google Analytics sets a first-party tracking cookie, which then leaked in a large number of cases to the third-party, to the CNAME-based tracker. So these leaks are not all intentional. However, We also found that cookies were leaking in the URLs of requests. So this indicates that the trackers could be performing cookie syncing, which is a tracking method where the cookie or the value of the cookie is explicitly shared with the tracker in the URL of a request to the tracker. This method is also meant to bypass tracking protections. And we found for the largest tracker, the largest Cname-based tracker in a dataset, we found that the cookies that were set by its third-party domain were leaked to the Cname tracking domain, which indicates that it is trying to sync the cookies. Further, we found that also some sensitive information was leaking from cookies that were sent to the Cname-based tracker. We did a manual analysis on 50 websites, including different Cname-based trackers, and we found that on 17 out of the 50 websites, some sensitive information was leaking. So a full name, a location, an email address of the user, and in 10 cases, the authentication cookie, which also has some security issues. And finally, we found security issues that were arising from the way that the Cname-based tracking scheme is set up. Because of the fact that the tracker is included in a first-party context, some major web security vulnerabilities were possible. So if the tracker would have been a third-party tracker, the vulnerabilities would not have been present on the website. But we did find two major vulnerabilities affecting all of the publisher websites that were using the specific tracker. So now I want to discuss some of the countermeasures against Cname-based tracking. So one of them is to block at DNS level. So in this case, we would use the DNS information of the request to determine whether the request will end up to being a request to a tracker or not, which is the case with uBlock Origin on Firefox, and Brave and Firefox themselves have also implemented this method. Another way to block Cname-based tracking is to limit the cookie lifetime, which is done in Safari. I believe that they set the lifetime of cookies to 7 days, making it more difficult for the Cname-based tracker to track the recurring users. It is important to note also that using a purely block list-based method without DNS information to block Cname-based tracking would be infeasible, because we would need an entry for each Cname tracking subdomain of a website. So this leads to a huge performance and maintenance cost. And furthermore, the websites themselves could also very easily change or even randomize the subdomains that they're using for tracking. So a pure block list countermeasure is not the most efficient way to go. So to conclude, I would like to sum up the main contributions of our study. So first of all, our methodology allows us to detect Cname-based trackers that were previously unknown to tracker blocking tools. We performed a large-scale evaluation of Cname-based tracking, and we found that the popularity of Cname-based tracking has increased with 21% over the past 2 years. And finally, we find some major privacy and security issues related to the Cname-based tracking scheme. Namely, we find 2 major web security flaws, and we find that sensitive information is leaking to the Cname-based tracker. Even emails and the full name of users can be leaking. So thank you for your attention. If you have any questions, I will be happy to answer them.